So shall we get started? So hi everyone, I'm Lidi from Google, and this is my GitHub account. And today I want to share a topic that I personally find interesting during our daily routine of helping people debugging their services. And I hope this topic will help you to build a more reliable service, like after it is done. And today we have three agendas. We are going to answer these three questions. What is flow control? Why is flow control important? And how gRPC solves it? Before we dive into the problem itself, let's refresh what is gRPC. So gRPC back in 2015 was designed by engineers who knows networking system quite well. And it has a bunch of powerful features that can ease the pain of developing distributed systems. And these are some highlighted features like bidirectional streaming, built-in flow control, load balancing, service config, interceptors, API contract. And today, we are going to dive into the built-in flow control. So what is flow control? Let's give it a definition. Flow control is the mechanism to throttle the traffic in order to protect the endpoints that are under resource constraints. So for people who are sitting here, if you have unlimited budget, sorry, this talk is not for you. And also some of you may ask, like, why do I want to slow down my traffic? Do you know how much effort I put into it to make it fast? So, well, to answer that, we need to realize flow control is all about scaling. Because first, it's common to see computational power difference between server and client. In microservice architecture, it is common to see a database node serving more than 100 different clients. And it's also common to see a web server is serving tens of thousands of devices at the same time. Also, the infrastructure has evolved a lot in the past decade. Luckily, we have Docker in 2013, we have Kubernetes in 2014, and this is the fifth KubeCon. So we are putting more and more fancy stuff into our architectures, like service mesh, side proxies, and various stuff. So every single request nowadays involving a large number of networking components. And neglecting flow control may cause outage in one of them, and it will be extremely hard to debug. Also, to make things worse, people love to maximize the concurrency of their application by using buffering, caching, or message queues, which I agree, it boosts the performance a lot, but also puts a lot of pressure on memory resources. So, in a word, if you are just writing unit tests or building toy projects, you don't need to worry about flow control. But if you are serious, you should pay attention to it. To better demonstrate the effect, I draw this diagram. Imagine you have a busy application. You can see it as a database node or a machine learning worker that is doing some heavy lifting work and cannot keep up with the sender. So what will happen is the message will be buffered up in the busy application until it's out of memory. So if the application is dead, which means no one is reading the buffer out of the kernel, and then the kernel will start to drop incoming packets. Then the message will start to buffer up on the sender side. Eventually, the sender application is also out. So in this way, the fast sender is sending so fast that it does not only overload the receiver, but also committed suicide. So the idea of flow control actually is very simple. So when the message is buffered up in the receiver application, all it needs to do is find out a way to signal the sender, please slow down. And the sender will respect this command and throttle its traffic. So let's take another look at this, at flow control. So imagine you have a sequence of services. If you don't turn on the flow control, which means all the service is sending at its full capacity, ignoring the fact that the downstream service may not capable of handling all of it. You may say, okay, then let's put flow control on some of the critical nodes. Does that work? Nope, because the pushback message is not sent from the and the receiver to the original sender of the request. And then you will have some fun time debugging like which one is the one to blame. So the valid solution of flow control has to be from end to end. Next, let's talk about the challenges of implementing flow control. So first, it needs to be performant because flow control is in data path. We do not want a protection mechanism that will slow down the traffic by 30%. It is unacceptable. And we want fairness between RPCs, which means we do not want a malicious client sending a malicious request and blocks an entire service. And also, we want the algorithm to throttle based on performance so we can utilize all the computational power and networking resources. Last, and most importantly, we want a flow control mechanism that can deploy from end to end. Next, if you still remember your networking system lecture from your undergrad, you probably will remember this. There is a similar concept to flow control, which is called congestion control. They are similar, but serving different purpose. The goal of flow control is protect the nodes inside the network, while congestion control is protecting the network itself. The trigger condition for flow control is when the receiver is slower than the sender. And the trigger condition for congestion control is low bandwidth and lossy network. And in real world, for most of the time, the flow control and congestion control are working together to protect your cluster. But if only congestion control is like kicking frequently, maybe it's a good indicator that you should contact your cloud provider. And next, since we're talking about congestion control, let's take a closer look at it, like how it works and why it is not the best solution. Quick side note here, if you are a Linux user, you can try to type in the command below to check your active TCP congestion control algorithm. Okay, back to the topic. So the common algorithms are Reno, Big, Cubic. I won't dive too deep into them. And the general strategy is very simple. It will increase the sending rate if ACK is received, and it will decrease the sending speed if ACK is missed, which means the packet has been dropped by switches, routers, or peer. In this way, the TCP can achieve flow control by doing following steps. When the buffer is filled up in your application, it stops reading from the kernel buffers. Then the receiver will drop any further incoming packets, and in this way, the memory pressure of the receiver will not get worse. Then the receiver is getting protected. Job done. But except there are two drawbacks. First, the sender is observing a lot of packet loss, which means it will think, maybe I'm in a really crappy network, so you will reduce your throughput and eventually ended up with higher latency. Also, it will effectively make the TCP multiplexing not working. Why is the multiplexing so important? Let me give a quick reminder to people who have forgot what is it. So imagine you are using your laptop and doing multiple tasks at the same time. And all the tasks is sharing the same network connection, and they're happy because they don't use a lot of bandwidth, until you're trying to download this 80 gigabytes again, which will effectively drain all of your bandwidth. And in this time, the upstream will try to throttle your traffic. But in front of the TCP protocol, it cannot differentiate like which task is which. So when you push back, all of the task is going to be pushed back, which means a misbehaving task is influence other normal tasks you are using. And it will be harmful also in data center case that a pod in your service mesh may be not responding to your control plan due to congestion control. So how do gRPC solve this problem? This is the gRPC solution, which is HTTP2 flow control. The algorithm itself is highly similar to token buckets. You can imagine the flow control window as a bucket full of tokens, and the sender will try to grab the amount of tokens as many as the size of the data frame. If the tokens is not sufficient, the sender will have to wait. On the other hand, the receiver can replenish tokens by sending window update frames, which effectively means I'm ready to read more bytes. As you can see here, this algorithm is highly performant because for the most of the time, the sender is not blocked by flow control, and it can send at its full capacity. Also, HTTP2 provides fine-grained throttling, which enables per-stream flow control and per-connection flow control. And the most important feature of this algorithm is the per-stream flow control, which means it enables the receiver to push back on the misbehaving RPC instead of all of them. Next, it also provides frame priority, which means the pushback only works on data frame. Instead, all the control frame can pass and can come through, even if it is under flow control. So the control frames are like window update frame settings, ping, reset stream, etc. So we already have the design. How hard can it be to implement it? Turned out quite hard. This is the quote from the RFC itself. It says, even with full awareness of the current network situation, implement the flow control can be hard. Failure to get all the details right may lead to deadlocks. So if you still remember, the idea of flow control is very simple. You just want to signal the sender to slow down. Why do we need to know all these complicated algorithms and comparisons? Well, you don't, because we got gRPC. And as we know, gRPC has three major stacks: gRPC C Core, gRPC Java, and gRPC Go. All of them are natively integrated with flow control. And in most languages, it is turned on by default. And here has two special cases for Objective-C and Java, because they want to provide a pure asynchronous API, which means the protection for the receiver is always on, but the protection for sender is opt-in. And also, the gRPC implementation is quite robust. It is validated in many productions. gRPC has adopted by many companies. And since I'm from Google, I can only speak for Google's use case. So gRPC is one of the cornerstones of Google's infrastructure, and it is handling tens of millions of queries per second. And next, during our real-world deployment, we found an issue with window size. Imagine the network as a pipe, and it takes time for data to flow from one side to the other. If we set the window size too small, which means when the data is floating from one side to the other side, the sender is idling, not doing anything, but waiting for the window update frame. And this phenomenon will get worse when your sender and receiver is not in a same data center. Maybe one is in East Coast, one in West Coast, one in Europe, one in North America. What we want here is we want the window size to be as big as possible to utilize all the networking resources. But we don't want it to be too big that it can overflow either side. gRPC's solution here is the BDP Estimator. So what is BDP? BDP is bandwidth delay product, which means the amount of data that can be in transit in the network, and the computation is easy. You can measure the bandwidth times the round-trip time, which effectively you can get the volume of the network, which is the flying bytes on the wire here. And this algorithm will measure the BDP and then set the initial window size to BDP. And by doing this, it can intelligently avoid triggering flow control. So let's recap what were the challenges we had before. So first, we need a flow control mechanism that is performant. Well, gRPC is performant. And we want fairness between RPCs. HTTP flow control supports multiplexing. And throttle based on performance. We got BDP Estimator. And last, flow control from end to end. gRPC has built-in flow control, which means by adopting gRPC, you are already protecting your cluster. So, problem solved. Everyone's happy. And next, let's take a look at how flow control actually works inside of actual code. So this is a snippet from gRPC Go. You can see this is a streaming call. And when you are trying to send something, the send API will block until the message is accepted by the flow control window. The same thing happened to the gRPC Python, that the yield statement will block until the message itself is accepted by flow control. Things is a little bit different with gRPC Java. For incoming traffic, it has automatic flow control, which means it won't request the next message until the existing one is consumed. And for outbound traffic, we provide two ways to handle the flow control. The first one is there is a flag called isReady to check whether the peer is ready to receive your message. And you can also set an onReady handler, which means if there is an opening, whenever there is an opening in flow control, it will invoke your callback. And even though flow control is great in most of the scenarios, some of you may still think, it doesn't fit into my scenario. I just want buffering whatsoever. Does that mean I cannot use gRPC? Well, no, because gRPC also provides message buffering in core and Java. So in core-based implementation, you can always flip a bit in the right option to signal the C core that this message does not need to be accepted by flow control window, and you can propagate it like as soon as possible. And also you can use the channel argument here to set the right buffer size. And if you really, really don't like BDP estimation and you know what you are doing, you can disable BDP through this channel argument. And in gRPC Java, for inbound traffic, you can disable flow control before the connection is even started. But the downside is that you need to call request int, which tells the framework that exactly how many requests you are going to receive. And you can call this API multiple times. For outbound traffic, to ignore flow control is simple. You can just simply ignore the isReady flag, but it may cause indefinitely buffering here, and maybe it will cause out of memory in your application, so use with caution. So, takeaway. Today we answer 3 questions, like first, what is flow control? Flow control is the mechanism to throttle the traffic to protect endpoints. And second, why is flow control important? Because fast senders may cause excessive buffering on both sides. And how gRPC solves it? gRPC provides easy-to-use built-in flow control. OK, that's all the content of this talk. I hope this will be useful. Yeah. And now I take questions. It can be related to flow control or gRPC whatsoever. Right. Also, there is a gRPC maintenance session. We will be held in the Google Community Lounge just after this session. If you're interested in gRPC, feel free to come. Yeah. Questions? Oh, yes. You can just shout, please. Yeah. You.
Hi.
Hi.
I want this flow control mechanism that you talked about in gRPC. Is that implemented in your client libraries for the cloud services like Bigtable and all that, like the client?
Yes. By default, it is turned on.
Okay. And what do you mean by infinite buffering when you mention on your slide?
Eric, do you want to discuss the infinite buffering?
What was the precise question?
The question is, can you explain like the infinite buffering for the outbound traffic on gRPC Java?
Yes, so there we go. The API in Java is fully async. That means it's not going to block, and that means that there's only a couple different ways that you can interact with it in order to deal with flow control. One way is we could throw an exception or something like that if you made us unhappy. There's a couple other sort of variations. But lots of times you might need to do, you get like a batch of messages all at once or something like that. You can go ahead and send them all to gRPC. Like if you were just going to hang on to them yourselves, and instead of doing that, you can just send them to the gRPC Java library, and it will go ahead and send them whenever it's able to. But the is ready and on ready will still be operating during that period of time. So you can send a bunch. You already have those in memory. They're now just queued. Whenever they actually get sent and whenever there's more memory available, then you'll still be able to get an on-ready callback and continue sort of to have your nice proper flow control. And so it allows you to have a little bit more bursty behavior. This is the primary reason that the infinite buffering is there, just because because of the way the API is fully async, it was sort of easiest way for a lot of applications, and it means the applications didn't need to buffer themselves if they were going to be buffering anyway.
Okay.
Hi, great talk, thank you. In the C#, in .NET Core, the C# version is now completely native. Do you know if they implemented flow control the same way as the C version, or is it yet another version like Java? Or
you mean for which language?
.NET Core 3.0, the gRPC client, is now completely native.
So I would expect it does not have any the bandwidth delay product measurements in place.
Okay.
Actually, we may be able to get a more authoritative answer on it. But I would expect it. Yeah. Do you want to?
Hi. So I'm the author of the .NET Core version of gRPC. So yes, we support flow control. Because it's just built into HTTP2, we support HTTP2, you get it. I don't know what other measurements you offer and other implementations, but we probably don't do that.
You probably have a default flow control window size.
Yes. Yeah.
And what is that set to initially?
I don't know. It's configurable on the server.
Yeah. So a lot of implementations might start at 64K as their initial window size. That works pretty well in. I mean, that might seem really small to some people. 64K. Wow. I eat that for breakfast or whatever. But that's actually a pretty good number for a lot of networks. It's quite surprising how many networks it is a good number for, because as networks tend to get faster, as in less latency, they tend to get bigger as far as pipes. And it just so happens that like monetarily, 64K is just sort of how those two things even out. The main case that doesn't work as well is whenever you've got big, expensive pipes, like between big data centers or especially cross-continent. Those tend to be very, very long, and because they're so important, they tend to be pretty big and fat as well. And so you may need to, if you're going over some of those pipes, increase the default window size. So the BDP measurement figures this out for you, so you don't necessarily need to normally, but for like an implementation there, you would get to figure it out. And you can end up monitoring your network if you know the throughput and if you know the latency just with ping. You multiply those together, and that's a pretty appropriate size. But like 64K, I said, is what you might default to. Some of these networks might need 4 megabytes or 8 megabytes. It really scales quite high on that high end, which is why we don't typically want to use all that memory. We want to use something less than that that's more appropriate to the actual network you're using.
Please.
Hi. Do you have any plan to officially support Rust?
Jayan, can you answer that question?
Not right now, but we welcome community contributions and we're happy to support.
Okay, please.
Are any KMX metrics being reported if throttles occurring?
Sorry, can you say that again?
Are any metrics being reported out if throttles is occurring on any producers' space?
What is recurring?
The metrics.
The
if throttling is occurring.
or throttling is occurring. We have one use case that, well, the people was confident, they turned off the flow control before, and after, like, because they're confident about what they're doing, and when you put it back on, they can observe a more than 50% decrease of latency.
I think there are some possibly trace settings in the environment you can enable, and it will put some logs.
I will note though that like here it's not necessarily bad whenever it's happening. It's some of this is normal, especially for burstiness behavior. It's very normal for like if you're going to send 4 megabyte message or something like that, you're going to get sort of temporarily throttled, but it's not actually harming anything because that's just the way the network will operate and stuff. So there you have to be a little bit cautious to figure out what you're actually looking at if you're looking at sort of if there's buffering like that. Because buffering is very normal. We're not trying to actually remove the buffering.
Is there a way to achieve flow control if we have a REST gateway in front of a gRPC server?
A REST gateway?
Yeah.
Well, the HTTP 1.1 flow control is done by the TCP congestion control, which means on that end you are not protected, but after the gateway it is protected.
Well, so the TCP flow control will still interact there,
yes.
Because that's just what HTTP1 used. And so if you're, let's say, doing streaming without like service streaming or something like that, TCP will interact fine, and then that can get converted fine into HTTP2 flow control and things like that. It depends a little bit if you're talking about like just doing lots of requests all at once, or more of a streaming situation. Oh yeah, yeah. Also, whenever you're going through things like that, every proxy, sort of everything in the middle, will have its own flow control, and so you might need to configure some of the proxy settings to be larger. So we said, like for example, the 64K I mentioned, proxies might have that as well, and you might need to increase it, or if you see they're buffering a lot, you might need to decrease it, that can totally come
So there's no direct way of leveraging gRPC flow control?
So flow control is sort of point to point, and then you add them all together and you sort of get end to end. I'm basically saying that there's existing flow control there, and it'll just work fine, because HTTP1 has flow control via TCP, and then it gets converted into HTTP2 flow control, and if it gets converted into something else, it can go as many times as you need in a sort of point to point. So it should all just be fine.
The gRPC load balancing, the feature, is that implementation of application, end-to-end application is like a replacement to the broker-based, like, you know, like message brokers, or let's say I mean, is that the solution to that, or, I mean, what's the feature?
So message brokers, part of what they do is load balancing, and so if you're using your message broker predominantly for load balancing, it can be a replacement to use the smart load balancer on client side. It's a little bit of a false dichotomy depending on exactly what you're using the broker for. The broker does provide other things. Commonly, though, you might not need those or not using them, in which case you can get sort of the cheaper as in cost approach of using the client-side load balancing, and that can reduce latency, and you can reduce the amount of I/O and stuff that's happening in the network.
Earlier it was mentioned that the flow control was like on a per stream basis. I'm a little confused because like I kind of thought the point of HTTP2 was to open up multiple streams and get a bunch of requests. So if I send like 100 concurrent requests, I'm assuming I get 100 streams.
Yes.
Each stream is flow controlled separately or together?
So the question is, if in HTTP2 every RPC will be open as a stream. So if you open up 100 RPC, does that mean this 100 stream is flow controlled separately or altogether? So in most of the case, they are flow controlled separately, which means if you are sending a large amount of unary requests, you can still overload your server in that way. And the per connection flow control actually is quite similar to what we have for TCP congestion control?
Yeah, and the short answer is both. And it does depend on the implementations you're using, especially whenever you're mixing in proxies and stuff. There is a connection level flow control, and there's also stream level flow control. But connection level flow control is a little bit, I'm going to say, not dangerous. I'm not necessarily saying that. It might be a little temperamental, because you can have the possibility that you end up starving streams because of some streams that are very active and they just steal all the flow control from the others. There's a couple different ways it can be tuned. There's a couple different things. It's a little bit more complicated, and in some ways it's more to protect your entire process's memory, and not as much this particular connection. You might bring it down for multiple connections at a time, or a couple different things. It's a very much more nuanced conversation. I think a lot of the implementations, I'm saying gRPC and outside of gRPC, are a little bit more simplistic there. I think C core has some very advanced things there, but it would be a whole nother topic. Yeah. C has a total memory limit that you can apply to it, and it'll bring down those connection windows in accordance.
Yep.
Is there any plan to move gRPC to HTTP3?
The question is there any plan to move gRPC to HTTP3? Jay, do you want to answer that?
Yes, when HTTP3 comes, I think Quick is kind of the basis, and we are thinking. We've seen benefits on mobile side, so that's where we are trying to use it, and then as our experience grows, we'll definitely think. Yeah, we have it on mobile platforms, Quick, which is not exactly HTTP3, but will become, hopefully, HTTP3.
Okay. No more questions? Okay. Then let's call it over. Thank you.